Yeah. And so today we're going to talk about how to find the area, but using some shortcuts. Because last week when we have to find little rectangles and then try to last week when we're trying to find the area by looking at the rectangle, um, by breaking the area down into different rectangles, and then try to add up all the rectangles, and then try to make the number of rectangle as many as we can, take that to the infinity. It's a lot of algebra, and it's not very simple algebra either. It's difficult algebra to work with. So what we are going to do instead is we're going to find some way to make it easier. The first thing that we're going to do to make it easier is so before we do that, we're going to go through an example to sort of emphasize the idea of finding the area underneath. And then we're going to sort of see what kind of connection there is and eventually lead us into the fundamental theorem of calculus. And this is very important. So we'll go back to the fundamental theorem of calculus a lot. The very first part, we're going to abbreviate it as FTC1. Okay, so here we're trying to find the area underneath a graph. And we're going to have this type of form. Okay, so for example, here g of zero would mean that, oops, I made a mistake. Okay, this part over here. Ooh, first typo of the course. Okay, so first typo that we know that this should be 0 here. Right, this should be 0. So we're talking about a function, and the function is the area from 0 to some unknown number. So if I have g of 0, that means it's the area from 0 to 0, because of the top 0 over here, of my function that's in the graph. Okay. And of course, that would give me 0. The reason is because if you start and finish at the same point, then it doesn't open up, right? So it's a straight line like this. So it doesn't open up and there's no width. The width is equal to 0 and so there's no area. G of 1 would be a little bit different. G of 1 would be something like this. We're going from 0 all the way up to 1, and that's the of our function, and we're trying to find the area underneath. So what we're doing here for g of 1 is that we are trying to find the area underneath here, and that happened to be a triangle. Width is 1, height is 2, so the area here is 1. So you kind of have the idea when we write it in this form, the variable here, t, doesn't really matter. I could easily have called it fu du. Wait, fu du doesn't sound very respectful especially when I record. But ft dt or fy dy, it does not matter what that variable is. Okay. But what you'll notice is that as I do the integration, as I try to calculate the area, the amount that we get, the area that we get. So g over here, you can call this the area, right? G of x is the area from 0 up to x. Then the area depends on where x is, right? Where we're always starting from 0 and where do we end. G of 2, it's easy to understand as well. G of 2 would be the area underneath here from 1 to 2. And what we would do typically when you see a geometrical shape is to sort of break it down into parts and try to find the area. So we know the triangle has the area of 1. the rectangle here has an area of 2. So altogether, g of 2 is equal to 3, right? The area is equal to 3. If you look back on assignment 1, in assignment 1, there's a graph of the velocity and asks you to find the distance traveled. We are doing something very similar. We're trying to find the area. Now, if I'm trying to find, say, g of 3, if I'm trying to find g of 3, then I'm trying to add the first part all the way down like that. I'm trying to find that. And of course, for this curve over here, for the curvy part here, we don't exactly know what the area is. So we might have to estimate a little bit. Let's call that 1.3. Let's call that 1.3. So we might say g of 3 is equal to 4.3. But what you'll notice, one of the main idea that we're trying to get through is that when I'm writing my equation in this form, notice that this is x is my variable, and my area here depends on where the end point is, depends on where we end in my picture. Okay, so let's go on a little bit. In the next picture here, this sort of shows us what the value is that we just talked about. And finally, if we have g of 5, we're going to add up the same idea as what we had before. So before we did 1 over here, 2 over here, 1.3 over here. And what you'll notice is that this shape, this first part over here, this shape, when we go downwards, is really the same shape as the one up top. So you notice these two are roughly the same shape, right? They're the same shape. So I'm going to call this 1.3 as well. And I'm going to call the other side, because it's symmetric, 1.3 as well. So we're going to do that. Okay. Now, when I'm trying to find the area, when I'm trying to find g of 5, which is the area from 0 to 5, what we need you to, so that what we want to remind you is that we do 1 plus 2 plus 1.3, but then the other two pieces are going to be negative, and they're going to be negative because the height over here is a negative value, right? The height of my rectangle. So if I try to draw a rectangle like this, right? If I'm trying to draw a rectangle like this, the height would be -2. So it's a negative height, so that's why the area here is negative. So that's something new that something that we did last week, and I want to remind you. So when we calculate everything together, we get 1.7. Now, if we think about each of these area. No, wait, hold on. Before I go on, if I calculate the area, here, g of 5 is equal to 1.7. Okay, so g of 5 is equal to 1.7. So we have 5 over here. I draw a dot. That's 1.7. Right, so I have a dot like this. This is the graph of g. This is the graph of the area. So the y value here tells me what the area is. The y value here tells me what the area is. So at 1, the area is 1, right? So we have 1 and 1 over here. At 1, the area is 1. And then at 2, the area is 1 plus 2 is 3, right? The area of this piece. The area of this piece is 3. So I'm going to be looking at 3 over here, at 2 over here, the y value is 3. Oops, looks a little bit ugly. And then at 3 here, we added another 1.3 onwards. So we'll have that. And then this will be a little bit over, so that's 4.3 roughly. Yeah, and so hopefully by now you get an idea of what we're trying to draw. We're getting 1.7 here. and over here we have 3. So you can sort of see that that's the graph that we are getting when I plot this. If you think about the meaning of these two graphs, we might say that the graph on the left is something like the change of uh, the ICU patients per day. Okay. So for example, when it's up at 2, that means today we have 2 extra people, 2 extra patients that came into the ICU, right? So during COVID, this is somewhat important. We are looking at how many how many patient goes into ICU during COVID, because we want to make sure people are not, we can help these people when they are really sick. Let's say change of as COVID patients in ICU. Right, so we're tracking the change in the serious cases every single day. You have something like that. And on the other side, this picture over here will refer to the total number of COVID patients in ICU. And the reason why we could have this type of relationship is if you look at 2 over here, if you look over here and see that we have 2. So if we look at this period over here, so during that day, there are new 2 patients in the ICU, right? There are 2 new patients that came into the ICU. So what do you notice happened? We have 1 person in the ICU and the number got increased to 3 because at the end of the day, 2 new people came in. So this is the change, 2 new patients, and then the total number jumped from 1 to 3, right? So from 1 all the way up to 3. So that's the idea. And then, of course, the next day, if you look at the next day, the number of patient goes up. The total number of patient goes up because we brought in another 1.3. Okay, it could be 1.3 thousand, doesn't really matter, or 1.300, 130, doesn't really matter. But we brought in 1.3 more that next day, so the number continued to climb, right? There are more patients entering ICU. And then when the number is going down, so when we are not getting new patients, in ICU, when we are letting people home out of the ICU, it's a negative number. And so you notice that the total number of cases, total number of COVID cases in ICU is going down because we let 1.3 patient, we lose 1.3 patient that day. And so the total went down by 1.3. And you can see the relationship between the area and my total graph, right? I build up these area, I add these area up, and then my value starts to go up, and then it starts to go down like that. And if we think about going up and going down, well, that is the rate of change, right? That's the rate of change. So when I find the derivative here, if I have this graph, if I have g over here, and if I find the derivative, that is going to give me f, right? Because this is the function of f, this is the function of f, this is the function of g. But it seems like f tells me how fast g is changing, right? F tells me how fast are we adding or subtracting the number of cases, and G tells me the total, right? So if I take the total, I take the derivative, I find the rate. So that's what we are trying to teach you in the fundamental theorem of calculus. When we integrate the final result here, the area function, if I take the derivative, that is going to be what's inside. So the inside is like the derivative, the outside is the antiderivative. So that's the reason why we went through this first little example, is to give you a rough idea. Okay, we're not doing a proof, but I want you to be able to sort of see the connection between the two. We're going back to the rate of change idea. Oh, by the way, if you ever want to take a screenshot and I move too fast away, just let me know. I can always undo my deletion sometimes. Okay, maybe not this time. Sorry, not this time. I can always undo my deletion and try to give you time to take a photo. So what we're trying to teach you in the fundamental theorem of calculus, in the first part of the fundamental theorem of calculus, is that when you see this, what you notice is that G prime is equal to F. Okay, so this part over here, this part over here is the most important part. Okay, when you see an integral, from a number up to x, the relationship between these two functions is the following. The derivative of the result is what's inside the integral, what is in the integrand. So to go from here out to the outside, we're going to do the opposite of finding the derivative, right? Because f, we have the f already. F is the derivative. We need to find g. G is the original function before I start doing the derivative. So we're doing the antiderivative. And another way to think about this idea is that if you integrate the function, so if I integrate the function, I get g, and if I take the derivative again, I get g prime, right? And g prime is f. And what this tells me is that if I integrate something and then I differentiate something, I get back to where I was originally. If I differentiate, I get back to where I was originally. And the consequence of that is it shows you that these two are inverse relationship. So if you think about all the inverse relationship that we know, the easiest one is this. If I take x, if I square it, and if I square root it again, I get back to where I was, right? So that's what we're doing here between integration and differentiation. And we can see that on the graph over here. Let's say I am trying to integrate up to 3, right? Let's say I'm trying to integrate up to 3. And then I get a number, right? I find an area, and I got a number. Here I got a number, 4.3. But if I then try to do the derivative, so right now I only did that. If I try to do the derivative, what we're trying to tell you is that that takes you back to the original value. So if I try to take the derivative here, so what's the derivative up here? The derivative is 0, right? So we know g prime of 3 is equal to 0. But we're telling you the derivative is, if I integrate it and if I differentiate it afterwards, that gets me back to f. So that's the same thing as f of 3. And what do you notice? F of 3 is 0. Oh, cool. F of 3 is 0, right? The y value here is 0. And it should make sense because we are at the highest point because we added area onto it, right? We added area onto it. And now we're not going to add area anymore. We're going to subtract from the area because now we're going to go below. So we're going to subtract the area. So I'm going to add, and then I'm going to subtract. And so that's increasing and then decreasing. So we're at the highest point, right? And so this point here crosses 0. So right at that moment, we're not adding anything. So of course, we are trying to sort of emphasize the relationship of these two. Now, most of the time, the only thing that we're trying to ask you to do, the main thing that we're trying to ask you to do here is to try to see the relationship between these two parts, between these two procedures. So one of the kind of type of questions that will give you is to focus on whether you understood the fundamental theorem calculus. So we might ask you weird questions like this. We might give you a function, right? And this function looks weird. And then and it looks weird because we have the x up here. You'll notice that normally we are not going to have x up there. Normally we're going to have a number, right? We're going to be able to integrate, find the area from 0 to some number, and then I can try to find the area underneath. That's not the case here. But we don't actually need g. We need the derivative of g. So what we're trying to do is we're trying to find g prime, right? We're trying to find g prime. So the derivative here, I know this looks a little bit strange, but that tells me I'm finding g prime. Right. Then what we're going to do is we're going to sort of realize this. Here I have a function. I'm going to integrate it, and then I'm going to find the derivative. Well, if I integrate and then I find the derivative, it's going to go back to the original function. It's like this. If I ask you, I have a function like this, negative pi plus 1. Oh, hi. And you're like, oh, sorry, square root of pi plus 1. And you might be thinking, I don't know what pi plus 1, I don't know what the square root of pi plus 1 is. And that's okay. If I tell you, if I ask you, what is the square of this thing? Then you would just tell me, oh yeah, it's pi plus 1, right? It doesn't really matter what I have, but I'm doing the opposite, so I'm going to get back pi plus 1. And that's sort of what we're doing. We're trying to integrate, and then we're trying to find the derivative. So these two processes cancel out, are inverse of each other. Now the one down here is a little bit different because you'll notice that we're trying to notice that the variable that we're interested in is different. The variable here is different. When the variable is different, we should do something slightly different. Okay, so let me ask you this. If I need to find the derivative of sine to the power of x to the power of 4, you might think to yourself at the beginning, this looks strange. It's not one of our rules. Our rules only tells me what to do when I have x. And what we taught you is, hey, that's okay. If you need to find dy dx, but we don't have x nicely over there, we could do dy du. We can do chain rule. We can do chain rule with dy du first, and then we can multiply by du dx. So we learned about that. We can leave that here. Not an issue. Now the second thing is this. We can only do integrating and then differentiating if these two variables are the same. They are different in this case. So they are different in this case. And then what we are going to do is we're going to do the chain rule. So we're going to, instead of do ddx first, let's do the derivative of x to the power of 4. So let's do that. Do the derivative of x to the power of 4, and this 1 x to the power of 4 secant t dt. Right, and then we're going to multiply by d, the derivative of x to the power of 4 dx. Right, and we know how to calculate that. When I have x to the power of 4 and I do the derivative of that with respect to x, I'm going to have 4x cubed. Right, so the 4 comes down, and then the power gets reduced by 1, 4x cubed. Now, what about the front? The front, you notice how we have, in this case, now the variables are the same. It doesn't matter where we start. We can start from 1, 2, 3, 4, 5. It doesn't really matter. But in this case, I have secant. I end up having just whatever's inside secant. But I'm not going to write t in here because I put it x to the power of 4. So I'm going to put it x to the power of 4 like that, times 4x cubed. We're going to put that variable right there to replace my t. Okay, so if you want, you can take a screenshot, but you'll notice that's what we have over here. It's not very clear. There, secant u times 4x to the power of 3, and then we should substitute it back. I forgot to write the substituting it back part. I'll try to add it back in the notes later on. So it should go back to secant to the power of 4. Secant x to the power of 4. Let me back up a little. So that's one of the things that we are going to need you to do to be able to look at these fundamental theorem calculus, at least be able to convert between the derivatives and the antiderivatives, that kind of thing. Okay. The second part of the fundamental theorem calculus, and of course, we didn't really prove it. If you're interested in the proof, look in the textbook. Your textbook has a proof that basically goes through the Riemann sum, the definition with the limit, and then we use some of the rules that we develop to eventually get to the result. The second part of the fundamental theorem of calculus talks about the definite integral. So if I know where I'm starting and if I know where I'm ending, we know that the function that we have inside, we can sort of treat it as the derivative, and then the outside is the antiderivative. So you notice that most of the time we'll write it like this. We'll sort of notice that the inside is the derivative of the outside. So outside we will use the capitalized letter to represent the antiderivative. And we're trying to sort of tell you that the big letter, the derivative of the big letter is the small letter. And we'll try to emphasize on this. This is the most important concept of our course. But most of the time, we don't actually use this directly, although it helps us check the answer. We should, at the very beginning, you should always double check your answer. And to double check your answer, you take your answer and you find the derivative to see if it matches with the integrand, whatever function that we start with. Now, in the first part of the fundamental theorem of calculus, we showed you that if I have a function and if I integrate it, then differentiate it. So integrate first, differentiate second, I get back to the original function. But notice how the function inside is the derivative of the outside function. We can think of it as I have taken the derivative first, then I do the integral, then that gets me back to the original function. Well, actually, not really the original function, but the difference in the original function, the change in the original function. So once again, because I differentiate first and then integrate, that give us back to our original function, even though it's the change in the original function. We can say that it's these two processes, integration and differentiation, are inverse of each other. So if I differentiate first, integrate second, I get back to the original. Same thing with integrating first, differentiation second. So it doesn't matter which order you do, you'll get back to the original function. Okay. So starting now, we're going to show you how we're going to approach the problems. So starting now, when we see an integral, we are not going to think about what does the graph look like. Well, we should still think about what the graph will look like sometimes, because that will help. But most of the time, we are not going to worry about the graph, worry about the rectangle. We're not going to do that. What we're going to do instead is we're going to find out which equation, which function is the antiderivative. And when I have e to the power of x, the antiderivative is e to the power of x, right? Because e to the power of x, if I take the derivative, if I take a look at this function over here, if I do the derivative, I get the original function inside. So you want to make sure that the antiderivative here, if you find the derivative, if you do f prime, big F prime, you'll get back to the inside function. Once you have once you have the big F function, we're going to find the difference between the two values. So we're going to find the difference. We're going to substitute 3 in, and we're going to substitute 1 in, and we're going to have e to the power of 3 minus e to the power of 1. Now, we can use any antiderivative we want. So e to the x will work, e to the x plus 7 will work, e to the power of x minus 3 will work, because all of them, if I find the derivative, I'm going to get to e to the x. But having all these constants in the back is hard to do, makes things a little bit harder. So we are just going to use the simplest one, usually no constants. So usually we don't put down any constants. Now what we'll normally write before I write down this is that we should write down what the antiderivative function is. So if I have one integral from 1 to 3 ex dx, we should sort of tell you that the antiderivative here is e to the x. Now e to the x is a little bit confusing, so let's sort of do something a little bit different. Let's say we have 2x dx. Right. And what we are trying to do here is we're trying to find the antiderivative, right? We're trying to find the antiderivative. So we're thinking about which function, if I find the derivative, would give me 2x. And the answer is x squared. Right. And you can sort of see this because x squared, if I find the derivative, if I call this f, then f prime, big F prime, will be 2x. So the inside is the derivative. So to come outside, we do the antiderivative, we go backwards. So every rules that we learned before in your last calculus course, we're going to do the opposite. We have x squared, but it's not just x squared, it's x squared, and then we have to put in all these different values. So normally, instead of writing down what f is, instead of writing down, oh, big F is equal to x squared, normally we just write the x squared here, and then we're going to do evaluate it. We're going to find the change. We're going to find the change, and I'm going to write 1 to 3. This means I'm going to find the difference when x is 3 versus when x is equal to 1. So I'm going to take the final value, the one at the top, I'm going to substitute first. So I'm going to get, so I am going to get 3 squared, right? 3 go into x, right? Just like this. This basically means big F of 3. But most of the time we will write it like that. Because when you're actually doing the antiderivative, it's easier to write down the formula, write down the function of your antiderivative, and then just try to substitute. And we're going to substitute 1 and substitute 3. So we're going to substitute 3 first. Then we're going to substitute 1, the number at the bottom, the limit at the bottom. Evaluated at 1, and we're going to put it in, and we get 1 squared. 3 squared minus 1 squared will be equal to 8. So that's the process of what we're doing. In this question, we can do the same thing. We can do e to the x from 1 to 3. And that's really the same thing as f of 3 minus f of 1. It's just that we're going to put 3 into e to the x and then put 1 into e to the x. And that's how I get e to the power of 3 minus e to the power of 1. So by convention, that's what we normally do. If you want, you can do a square bracket, some textbook, and occasionally we'll do that if the result of our integral is a long piece of function with addition with different number of terms, then we will use the square bracket to put everything together. So we can also do that. If it's just one term, we get lazy, and most of the time we will just write a straight line and then the two value that I'm evaluating. So that's the process. Okay, and let me say one more thing. Let me say one more thing before I give you some time to try a few practice questions. Oops. Before I go on, if you want to take a picture, you can do that. And then I'm going to go on to the next page. So we're getting more and more. We're trying to to emphasize the relationship between the integrand and then the antiderivative that you get as the result. So here we have a slightly different example. We're going to integrate this function dx over x from 3 to 6. Now this one looks a little bit strange. So what we want to sort of tell you is that when you see this, this is the same as, remember dx is part of the integral notation. So dx doesn't really do anything. So that means we have 1 over x as the integrand. The function that we are trying to integrate is 1 over x. And then, of course, the dx isn't really doing anything. It's just telling us the independent variable here is x. Next, we want to think about which function has the derivative of 1 over x. And it turns out you'll have to remember this one. This one is natural log x. Now we're going to put the absolute value on because normally if I don't put any numbers in here, the limit of integration can be negative, right? Can be a negative number. But natural log, right, 1 over x is defined everywhere except at 0, right? I can put in positive 1, I can put in negative 1. But natural log, however, is only positive. So for us to sort of make the two parts equal, we're going to have equal range. We're going to put the absolute value around x in the natural log to make sure that we cover values lower than 0. We're going to do that. And of course, we can pick any, we can pick any, we can have +3, -2, but we're going to pick the easiest one, which is without any constant. Now we're going to evaluate this at 2 different values, as 3 and 6. So that's what we're going to do. And you notice what we're going to do is, when I put in 6, that's natural log 6. I don't need the absolute value anymore because absolute value of 6 is 6. Same thing as absolute value of 3. Absolute value of 3 is still positive 3. So we're going to have natural log 6 minus natural log of 3. We can put them together, divide the inside of the natural log, and we're going to have 2. Natural log 2 is the answer. Now, if you don't know how to use the logarithmic rules, it's really not a big deal. For our course, if you can get to here, because this is not, we want you to know it, but it's not super essential. But if you can get to here, that might be good enough on the test. Might be, depending on the question. Okay. We're going to mention one thing from 5.4. Now that we sort of established the relationship between integral integration and differentiation, we need to sort of have a convenient way to show that we are trying to do the antiderivative. Because to write that, if you think about, oops, okay, sorry, I don't know, I did not know the shortcut is doing all these things. All right, so if you look at what we're doing here, we need to sort of show you, remind you that the antiderivative of 1 over x give me natural log of x. Now, the other way is really easy to do, right? In the other way, on your differentiation table, differentiation rules, you probably have seen this before. If you have natural log x, right? If you find the derivative of natural log x, you get 1 over x, right? And remember, we have a nice table. We have a nice table of that. Let me see if I can. I'm going to see if I can find the table for you. So I want to remind you that when we. So here I have my table. Yeah. So in my differentiation class, I will give them the table that look like this, right? So it will tell you that if I have natural log of x and I do the derivative, I'm going to get 1 over x. So that's sort of what I'm talking about when I talk about these differentiation rules. What we're trying to do here is we're trying to have a way of expressing the opposite. So I know that the derivative of natural log of x is 1 over x. We want to be able to have a convenient way of showing you that the antiderivative of 1 over x is natural log of x. And the way that we're going to show you is by this notation. We're going to say, oh yeah, if I have 1 over x, and then I'm going to do the antiderivative of this, find the area, try to do the antiderivative of this, you'll get natural log of x plus c, plus some constant. And we have these constant because when you do the derivative, the constant just disappears, right? So it doesn't matter what constant we have. It can be 1, it can be 2, it can be 3.5, they all disappears. This particular notation is just the opposite of trying to write the differentiation rules. Yeah, so we will write it like that. And we call that indefinite integral. But we're not really integrating yet because there's no limit, right? If you think about what integral means find the area underneath the curve from one place to another. Here, there's no value written. This is just like a way of telling you, hey, we need to find the antiderivative. This is the antiderivative. But we're not really, this is not really a representation of an area. So one of the things that we can write is we can write, for example, x squared, if I'm trying to integrate this, the antiderivative, the reverse of finding the derivative would be x cubed over 3 plus c. And we can always double check, right? If I find the derivative of x cubed over 3, then I get 1 over 3 and then multiply by 3x squared. All right, because x cubed becomes 3x squared. So you can see that we get x squared, right? And then if I have plus 5, right? Then the 5 just disappears, so I don't have anything in the back. So in the end, I get x squared. So we use these indefinite integral to represent a whole bunch of functions and what the result will be when I try to integrate, when I try to find the antiderivative. Now to help you out, so here comes the important part. To help you out for the problems, you are going to have to know the opposite to all the differentiation rule that you learn. Well, at least the basic ones. Not the chain rule yet, but the basic differentiation rules, like the ones with sine and cosine, right? Because you have to know derivative of sine is cosine, the derivative of tangent is secant square, the derivative of secant is secant tangent. And so you see that they are placed in a backward order, right? So instead of writing derivative of sine give you cosine, I say doing the antiderivative of cosine gives you sine. Antiderivative of sine gives you negative cosine because there's a negative part in here. You don't have to worry about the hyperbolic. You don't have to worry about the hyperbolic one. They're not in there. Well, at least I didn't really cover these function when I was doing calculus 1. So it's okay if you don't know these. And we'll try to provide you with the table during the exam as well. But most of these, just like the differentiation rules, you'll use them so often that you should know them. And that saves you a whole bunch of time because the method is going to get more and more tricky, and it's going to be difficult to do. Now, some of them, the top 3, we have talked about them last week, sort of, in properties of the integrals. So these are properties of the integrals. If I have 2 different parts, I can separate them. If I have a constant, I can pull it out in front. It doesn't affect my integral. So that's the same. It's very similar to doing derivatives. And if I have a constant, that becomes constant times x. This part we haven't really talked about. Okay, so I should say that the first two here we learned before. No, this one is the most common and important one that you'll need to know. This is the opposite of power rule. So what we are going to do, if I have x squared, the antiderivative is going to be 1 power higher, because when we do the derivative, we subtract 1. So if I'm going back, I add 1. So it's x to the power of 3. But not only that, when I do the derivative, there will be a constant of 3 in the front, right? So if I'm going backwards, I need to make sure I divide that constant out instead of multiplying. So that's why I will, instead of -1, instead of taking the power and subtract it by 1, we're going to add 1 to it, and we're going to divide by that power instead of multiply. So that's what it looks like over here. And finally, when you do these antiderivative, just always remember there's a constant. You can put any constant here. You can go +1, +2, +1/2. It does not matter because the constant will go away and the derivative will still end up being x squared. So we'll write it like that. So that's what this rule tells you. If I have x to the power of -2, so similar idea, if I have 1 over x squared, when you do the derivative, you need to make sure that you think of it as a negative power. When I do the integral, I need to think of it as a negative power, just like below here. I need to think of it as a negative power. And when I do that, if I have power of -2, when I add 1 to it, that's x to the power of -1, right? And then divided by -1 plus c. But normally, I don't write x to the power of -1. I write it as 1 over x. And normally, I don't divide it by -1. I write the division sign in the front. So that's how we end up with this result at the end as the antiderivative. One of the things that we need to remind you is the following. We need to remind you that when I have 1 over x squared, the function looks like this. 1 over x squared, the function will look something like this, right? I will have a very big number, and then I'll have, when it's small, I'll have a very small number when it's big, right? So if I have 3, 1 over 3 squared is only 1 over 9, very small. But when I have 1/3, if I flip it, do the reciprocal, I get 3, and then I square it, I get 9, it becomes very big. I can have negative number as well. So I can have the other side. And when we've written it like this is sort of saying that it works everywhere, bigger than 0 and less than 0, but it does not work. But it doesn't work at 0. It doesn't work at 0 because 1 over x squared is not defined at 0. We didn't bother writing that part there. Okay, we didn't bother writing that part there. But it is sort of implied. You should understand that this function works, but it doesn't work at 0. Okay. So if you try to do an integral from -1 to 3, and then you're like, oh yeah, it doesn't work. Well, yeah, it doesn't work because it doesn't work at 0, and you can't do that. Okay, you can't find the area here when there's a point in the middle that doesn't work. That's undefined. So that's sort of one of the small issues that we might run into when you're actually doing it. Another common mistake is to realize that if I have integral of 1 over x dx, we are not going to do power rule like this. We're not going to add 1 and have x to the power of 0. We're not going to do that because when I have 1 over x, the integral is natural log x, right? The antiderivative is natural log x, because if I take the derivative of the natural logarithm, I get 1 over x. So if I go back, that's the one that's going to work. And if you use the power rule, it will not make sense because you have x to the power of 0, you have a constant. And if I take the derivative of a constant, I can't get 1 over x. Okay, so now from now on, what you'll have to do when you see an integral is to think, which function gives me the derivative that's inside, or what is the antiderivative? So that's what we need you to do. So, yeah. Before I give you some time to practice, okay, let's look at one final example. When I see an infinite integral, or if I see numbers down here, and I'll show you what happens if I see numbers, say 1 to 2. What we are going to do is we're going to think, how do I find the antiderivative? How do I find the antiderivative here? And one of the things that will help you sometimes is to sort of think about what will happen if I take the derivative, because they're kind of related, right? So one of the things that you'll realize is this: the 10 doesn't matter, right? The 10, I just leave it outside. I don't deal with the 10. And then the subtraction means I do these two parts separately, right? I do these two parts separately. So first, I just have to find out what the antiderivative of x to the power of 4 is. And we're going to use the power rule, the reverse of the power rule. 4, I'm going to add 1, so that the power is 5 now, x to the power of 5, and we're going to divide by 5. So this part turns into that part in the antiderivative. Then we're going to look at the secant. Oops. We're going to look at the secant square. Secant square, which function has the derivative of secant square? That's tangent. So we're going to have secant square turning into tangent, and we left the 2 outside, right? We kind of ignored the 2, we leave it as a constant. And finally, I have these 2 parts. I found the antiderivative of that. And just remember, we need to be able to add a constant. If I have the indefinite integral, if there's no numbers here, you have to add c as your result. Okay, that's the general form. And finally, we would normally clean it up a little bit and have 2x to the power 5 minus 2 tangent plus c. Now, one of the things that I want you to be able to do is the following. At the very beginning, if you're not used to doing the antiderivative, after you find your answer, take the derivative. So find the derivative of that. The derivative will be 2 times 5, 10x to the power 4. And you're like, oh, this is good. This looks this looks right. Right. Minus, right? I leave the minus when I do when I differentiate. And I leave the 2, right? Just like how I left the 2 when I integrate. When I differentiate, I leave the 2. The derivative of tangent is secant squared. And we can sort of see that we got back to the function that we started with. Plus c goes away, it's a constant. And if you have, and now I just want to sort of remind you of the difference between an indefinite integral and a definite integral. So if we have, say, 1 to 2, if we're trying to integrate from the limit of 1 to 2, what we will do is when I find the 2x5, when I find the 2x to the power of 5 minus 2 tangent, we're not going to write the c because it doesn't matter what the value of c is, right? So it doesn't matter what it is, so we're going to not write it. We're going to now evaluate it from 1 to 2 or 0 to 2, doesn't really matter. Let's do 0. 0 is a little bit easier. And what we're going to do is we're going to substitute the top number. We're going to substitute 2 inside. So 2 times 2 to the power of 5 minus 2 tangent of 2. Okay, and that's the first part. And then I need to minus 2 times 0 to the power of 5. So that's just 0. Minus 2 times tangent of 0. That's still 0. So these two parts here at the end is 0. So we're going to be left with a number in this case, and we'll simplify the number. We'll get 2, 4, 6, 2, 4, 8, 16, 30, 64. We'll have 64 minus 2 tangent 2. Yeah, so we'll have something like this. Whoops. Yeah, so we'll have something like this if it's a definite integral. And if it's an indefinite integral, we would do the question the other way. Okay, so that's the main idea.